Hello. The next speaker is Lykle Voort, and he will talk about dynamic virtual private clusters with OpenNebula and SGE.
Hi, good afternoon. Is everyone? Or do I still have to wait for people to come? Otherwise, I think I'll just start for those who are interested. My name is Lykle Voort. I'm from SURFsara, and I will talk about creating dynamic virtual private clusters with OpenNebula and SunGrid engine. You may wonder what the SunGrid engine is for, what dynamic virtual private clusters are, and I'll come to that. Before I describe what they are, I want to describe why we developed them. And before I describe why we developed them, I think it's good to give a small introduction about what SURFsara is and what I do, so you'll understand the why. SURFsara provides computational resources to academic institutions, so universities, colleges, and mainly for research. We do supercomputing, cloud computing, and some big data infrastructure such as Hadoop. So let me give an overview of what we have. We have Cartesius. It's our most famous supercomputer. It's a Dutch national supercomputer, 40,000 cores, and this year we reached the 45th place in the top 500 of supercomputers in the world. We have our national cluster, 9,000 CPU cores. We participate in the grids, for which we run some of the Large Hadron Collider data crunching, and we also have a small national grid for the life sciences. We have a Hadoop installation for crunching big data, and we have the cloud, which I will be talking about today. Currently, we have 30 machines with 32 cores, 256 gigabytes each, and we have a couple of smaller nodes, but those are mostly for services. The cloud infrastructure is basically set up as follows. We have a network, 2 times 10 gigabits bonded. We have the smaller nodes that I was talking about. We have the 30 large compute nodes, and we have a couple of virtualized services. And as data storage, we use 800 terabytes of DDN storage exposed to NFS. We run a somewhat older version of OpenNebula. We run 3.2, which is embarrassingly old, but it's been running, and we're planning to upgrade to use the latest features, but we have not yet been able to upgrade due to our own customizations. Now, who's using our clouds? Fortunately, the colors are not really the PowerPoint colors didn't survive the LibreOffice treatments, but I hope you can still read it. We have a big part of our cloud users work in cell genetics. We call it life sciences, but it has to do with chemical processes within the cells, so DNA, RNA analyses. We have some linguistics, medicine, economy, marketing, ecology, some civil engineering, physics. So you can see that we have been able to reach a pretty big audience, pretty diverse audience. And in a sense, in one way, that's of course very good, because we've been able to reach the non-traditional supercomputing sciences, as opposed to, say, the supercomputers, which are mostly used by physicists, astronomers, the traditional supercomputer users. But at the same time, what you don't see here is any systems administrators. And that is not so good, because what we thought, we designed our cloud for small running jobs, short lifespan, mostly compute intensive jobs for, say, the traditional grids, what the grid used to do, building small clusters of computers. But now we have this huge group of scientists who run all kinds of jobs, who use long-running jobs, who want to run something for a month or for 2 months. They have one job that runs for 2 months. Or we have economists who use 50 terabytes of data, and they want to process 50 terabytes of data. So the initial target audience that we had in mind, like small jobs, it didn't happen. On the other hand, it's also good because the flexibility allows users to run whatever they want. Because our scientists really like to install their own software somehow. They don't like the pre-maintained system that our other infrastructures offer. But recently, IT departments, they contacted us, and they came to us with the following question. They said, "Now we have a cluster in our data center, but it's getting old. We're going to decommission it. It's getting out of support, and we would like to buy a new cluster, but buying hardware is so 2010. You guys have an HPC Cloud. We would like to run our cluster in your cloud." And in fact, that's quite sensible, because we get the IT department, we get some expert users. They're not the scientists who have absolutely no clue how to maintain a Linux operating system, or worse, a Windows operating system. But we have an actual IT department who they want to install a cluster in our cloud, and they're going to install it for their users. That's good. Now, what is a typical cluster? I don't know if you guys know what a typical cluster is, or what clusters are for. Clusters are lots of worker nodes, lots of machines that perform calculations. And generally, there's one machine that you can log into. It's usually called the login node or the user interface. And on the login node, you start your jobs. And the jobs get submitted to one of the available nodes. Generally, there is always a centralized user administration. There is a centralized home file system, which is shared on all machines. They generally have a local disk for scratch space, for fast I/O. And the jobs are scheduled using a job scheduler. Torque, PBS is Torque and PBS is one of the older ones. Slurm is used on one of our systems. But more recently, there's a Sun of Grid engine, which is the successor to the Sun of Grid engine. The Sun Grid engine, developed originally by Sun, and after Oracle bought Sun, the Sun of Grid engine guys decided they wanted their own version that would remain free forever. And usually, clusters are fixed size. I mean, it's 10 machines or 20 machines from the moment when you buy it until you decommission it. And it's always on bare metal. Now, as I said, fixed size is so 2010, because the guys who want to get our cluster, they say, well, sometimes we use a small bit of it, and sometimes we want peak capacity, and it's 2014. We want cloud. We only want to pay for what we actually use. So we want a cluster that scales automatically. If in quiet times around Christmas, you have a small cluster, and before the submission of the deadline submission for papers, we want a really big cluster. And we would preferably have it scale automatically. Let's see. So that's why I developed some sort of bridge between the SunGrid engine and between OpenNebula. Let's see. I wrote a typical job which users want to do. It's nothing exciting. It's generally a script. Does some work in the script and you submit it. So it gets submitted to one of the nodes, get executed by the node, and when it's ready, sends back the results. Now this job just sleeps for an hour, but in general, of course, the jobs will run some genetic analysis for, say, 10 hours. And if you have a lot of jobs, they fill up a queue. If you have more jobs, than the system can handle, then the queue becomes bigger, and you have jobs in the queue that are waiting. So that's what I do if I want to scale. If I want to determine if I need more nodes, then I just look at the queue. Let's see. I wrote this queue monitor. It's about 400 lines of Ruby code, and it runs within an event machine main loop. I don't know if you've ever heard of event machine. It's some sort of the reactor pattern. It allows you to have multiple processes within one program, and they all get handled in turn. Actually, all within one thread, unless you explicitly specify that you need it in another thread. I frequently poll the job queues to see if there are any jobs waiting. If there are many jobs waiting, then I use the OCA to start a node or to stop a node. And then I use QConf, which is a configuration tool that comes with SunGrid engine or SunGrid engine to remove or add a node. And I've written it down in a small workflow. It's actually a really simple workflow. I inspect the queue occasionally. If there are jobs waiting, if there are many jobs waiting, then didn't really come out. Anyway, if there are jobs waiting, I use the Ruby OCA to start a new virtual machine. I occasionally poll whether it's actually booted because it goes through the boot process. It starts with a couple of daemons. Once it's completely booted, it tells the scheduler that the machine has booted. And it adds the node to the nodes that can run jobs. If it hasn't booted yet, it just waits. And the opposite is also true. If there are nodes idle, I keep inspecting the queue. If there are any nodes idle for some time, apparently they can get removed. Which means that I tell a scheduler to stop scheduling jobs on that particular node, and then I have the Ruby OpenNebula Cloud API shut down the virtual machine. It isn't anything fancy, but it's actually quite simple. I don't use anything like contextualization because I wanted to keep it very simple for the end users. It's mostly a recipe for end users. They can add as many nice things as they want. I just wanted to keep it really simple. Does it work? Well, yes, in principle it works. But like I told you, our design, I don't know if you remember this slide from before, we have one big data storage, 800 terabytes of NFS shared file systems, and I took a screenshot yesterday of our load on the file server, and the red line is the number of processes, processor cores it has, and the gray line, the gray area, is the actual load, which means that our file server is getting hammered, which actually slows down quite a few of our machines. And I think with our current design, we've reached the limit of our clouds. We have about generally we have about 100 users. We have about, I think, an equal number of virtual machines running. So this is not just this little program, but this is also all other users who are using our cloud. It's quite busy. So I think we need to do some serious hardware upgrades, which we are going to do quite soon. To improve the utilization of our cloud, we're going to upgrade to OpenNebula. Well, we don't know which version exactly yet. I hope it's going to be the latest version, 4.10 or hopefully 4.12. Maybe by the time we're ready to upgrade, 4.12 will be out. We're going to get some more compute nodes, and we're going to add Ceph storage to our current setup, because I think it will really help us to scale to a bigger setup and to allow more users to run their virtual machines. We're going to add local SSDs, because the local scratch is really important if you want to get good I/O performance. Because we've noticed that our users, we don't know what they're doing, we don't want to know what they're doing, but we know they are using a lot of I/O. And if one user is using a lot of I/O, then all 100 other users are suffering from it. And finally, we're going to add some GPUs for those users who need some special computations that require GPUs. To summarize, was it easy? Was it possible? Well, the integration between, say, the Son of Grid engine and OCA, the OpenNebula and OpenNebula using the OpenNebula Cloud API and XML RPC, it was possible and it was flexible. I do agree that XML RPC is kind of difficult. I had some trouble finding working examples, but eventually I got it working. Once you get it working, it's quite flexible. Also know what your users want, know what they do. To use the previous example earlier today, are your users expecting kettle or are they expecting pets? Well, we find that most of them are using pets and they really value their data and their calculations. Any questions? Yeah. Well, we are going to add them to virtual machines. I'm not exactly sure. I'm not the administrator. I mostly talk to users and develop solutions for the end users. I know our cloud guru said it was possible. We'll probably have to do it on an individual basis. So we'll have to, once a user wants it, we have to schedule him or her on a machine that has the GPUs and then do some manual connection. We don't have that many users, so we know all our users. Other questions? Yes. No free resource. Yes. Yes. So I'll repeat the question. The gentleman asked what happens if we don't have any resources available? What happens if there are no more job slots available if we have any? Because we have users who would like to scale to infinity. Our customers don't pay. So we work on a first come, first serve basis. If there are no more resources, then there are no more resources. So I wrote on a rather simplified version. We do have some sort of manual scheduling. We know how our users request a certain amount of compute time, and we try to balance it to what we have available. So we review every application, and in fact, I think we're looking forward to the next OpenNebula version where we can limit how much users can use amid virtual.
We're doing more or less the same things, the same stuff you are, so we keep in contact.
Yes, sure. Any more questions? We're going to add SSDs to our KVM nodes, yes. Yes, the gentleman here asked if we are going to add SSDs to our nodes, and yes, we are going to add SSDs to our nodes. We are not going to add them to Ceph. We're going to add them as local scratch space, because what we see is that users, either they want to use a lot of data, which has to have some decent performance, but if you want a lot of data, you're not going to get fantastic performance. If you want really good performance, you're limited to a small size. So what we want to do for our users is that they need to process their data in small chunks. If you want 50 terabytes and it has to be really fast, that's too expensive for us. So it's either small and fast or big and okay. Any more questions? No? Yes.
You missed some of the first slides. You have 10 gigabit, not 9 gigabit.
No, we have 10 gigabits. Yeah, that's right. We actually have, all nodes are connected using, all hardware nodes are connected using two 10 gigabits. Two per node. And we have a very expensive switch which offers non-blocking and everything. So, but it's not InfiniBand. No. Any more questions? No. Thank you very much for your attention.